Today I will teach about UART programming, and let's do about transmitting data. So let's write a code. This line is including this library, and this library mainly focuses on the weight of the integers that are type 8-bit, 16-bit, 32-bit, 64-bit, the weight of the integers that are type. That's because we are using many 32-bit integers here in Cortex M4 microcontroller. So because of that, I'm using the 32-bit in data types. So I'm including this library because of that. Here I'm just including the library of M4 microcontroller on Cortex M4 bus, so that I can use all these calls, objects, whatever. I'm here writing the functions of transmitting data. But let me explain this function little bit later in the flow of the code. This is just a delay code, and let me also explain this function a little bit later with the flow of the code, because it will be more easy for you to understand. This is the main function. I'm just taking a variable C. This is 0 in hexadecimal, and this is 1 in hexadecimal. Now the system control is saying that the system control is using this RCGC GPIO, and its value is equivalent to 0x01. 0 in hexadecimal is this, and 1 in hexadecimal is this. Here this RCGC GPIO is a 32-bit register, and it seeks to supply clock shows to any one of the bits from bit 0s to bit D5. If you have supplied the clock shows to the bit 0s, that means you have chosen port A or GPIO A. If you have supplied the clock shows to the bit 1, then you have chosen port B or GPIO B. If you have supplied the clock shows to this bit 3, then you have chosen port 3 or GPIO 3, and so on. Here I supply the clock shows to the bit 0, so I'm using port A or GPIO A. The next line is system controls. Is now using RCGC UART, and its value is equivalent to 0x01. 0 in hexadecimal is this, and 1 in hexadecimal is this. Here the system control is using RCGC UART, and RCGC UART says supply a clock shows to any one of the bits from bit 0s to bit 7, and choose a particular UART modules you prefer. Here I'm supplying the clock shows to the bit 0, so I'm choosing UART modules 0. But if you supply the clock shows by setting it to 1, the clock shows in this bit 1, then you have chosen the UART 1. So if you supply the clock shows to this bit 2 by setting it 1, then you have chosen the UART modules 2. Okay? But here I'm supplying the clock shows to the bit 0 by setting it to 1, so I have chosen the UART 0. So I have chosen the UART 0. Let me initialize this UART 0. Okay, UART 0 is now using the control register and its value is equivalent to 0. So that means all the bits of this control register, which is a 32-bit register. 32-bit register means it contains 32 bits, and all its value is equivalent to 0. That means some of the control register bits are reserved, which even though we have put the zeros here, some of these control register bits are reserved bits and that we cannot change. Even if we write zeros here, it means that this which can be changed is all turns to 0. Okay, so let's say this 3 bits, we write this one 0, we write this one 0, but please kindly pay attention here. This UART enable bit is a bit that will enable UART, but here it is 0. That means UART is disabled. If UART is disabled, all these control bits will no longer work, right? So the main focus will be UART enable or disable. So UART is disabled here. So this means UART is disabled mainly. We will focus to it. Okay, and disabling the UART is necessary before setting up everything. Okay, so we just want to set something, all the setup first according to our desire or the general rules that preferred by everybody, and after that we will enable the UART. So let's disable this UART for some time, and this is a necessary step, okay, before setting up anything about UART. Let me explain this two lines together, this line and before line, because it only represents one thing. Okay, let me explain this two lines together because it only represents one thing. Okay, so let me explain how it represents only one thing. You will know it when I explain. Okay, so listen. Okay, this is something you must know. The baud rate. The baud rate is rate of data transmitted in the transmission medium or in the transmission process. Means the rate of bit is transferring, okay, or the speed at which bit is transferring in the transmission medium of UART. Okay, so that's the definition of baud rate. Alright, so let's see. So what is baud rate? Baud rate is speed of data transmitted in the transmissions medium or the speed of bit is transferring in the transmission medium. Okay, So that's actually the baud rate. So baud rate can be calculated using the following formula. So this is the formula. Baud rate equal to system clock by 16 multiplied by clock dip. This is a multiplication symbol, okay, not underscore. Don't confuse with that, okay. The system clock has the default value of 16 MHz. The default system clock value is 16 MHz, so we will just put the 16 MHz in the system clock. Then this line becomes this line. Here I'm just putting 16 MHz again instead of this. And then this is multiplication symbol. This is 16, okay, multiplied by clock dip. We will just cancel this 16 and then this 16. The 16 and this 16 is cancelled, then it becomes 1 MHz by clock dip, because this is just multiplication symbol. So we get here 1 MHz by clock dip. Okay, listen carefully. I'm putting the clock dip value here 9600. This is the value of the baud rate. Okay, and listen, this megahertz is a higher unit of frequency. Okay, let me reduce to standard unit of frequency hertz. 1 megahertz is 10 to the power 6 hertz, so this is 10 to the power 6 hertz. Okay, 10 to the power 6 hertz by 9600. Okay, let me explain here something more. Here, the left-hand side of the equation is baud rate. This is the right-hand side of the equation. Okay, this megahertz is only a unit. That means it is only 1 by 9600. That means the only term left here is 9600. So this is the value of the baud rate. This is left-hand side of the equation, the desired baud rate. And so this becomes the value of the baud rate. Okay, so you will find in some book the baud rate 9600, okay, 4800 as the value of the baud rate. Okay, so that's why it is written here as the value, okay, instead of, okay, as the value of the clock dip. This megahertz is a higher unit of frequency. Okay, and so let me reduce to, okay, standard unit of frequency. Standard unit of frequency is hertz, and 1 megahertz equals to 10 to the power 6 hertz. So I'm writing here 10 to the power 6. 10 to the power 6 means 6 times, okay, by 9600. This expression is saying 1000 bits sending at the baud rate of 9600. Okay, as this left-hand side suggests speed of, okay, data transmit, the rate at which data is transmit. So here, okay, 1000 bits is sending at the speed of 9600. Okay, so this is the things I have written here. Again, this is sending 1000 bits at the baud rate of 9600. Okay, let's consider sending only 1 bit. So instead of writing 1000, we will write only 1 bit. 1 bit by 9600 means sending of 1 bit at the baud rate of 9600. And what does it mean? Okay, this is 1 bit and at a baud rate of 9600. Okay, so let me explain. 9600 means signal here. The term 9600 here means signal changes 9600 times per second. Means that signal is from the in a graph, signal is from the like this, right? Signal is from the starting to the end of the one full cycle in the of signal in the graph. I think you know that, right? Everybody must be knowing. So that is one cycle of signal. It changes 9600 times. Okay, this 9600 represents the signal changes 9600 times per second. Okay, so let me write, instead of 9600, let me write 9600 number of signal changes per 1 second. In mathematical expression, I can put this in the numerator, right? I can put this value in the numerator, right? So I just put that 1 second here. Okay, then it becomes like this. Let me convert this 1 second to microsecond. 1 second equal to 10 to the power. If I reduce to microsecond, it will be thousand microsecond, right? So it will be thousand microsecond. This thousand microsecond, if I divide by 9600, I get this much microsecond, which means it takes 104 microsecond to send 1 bits. Finally we get this much second, and this is often from when we consider only about sending 1 bits. So sending 1 bits takes this much microsecond. Alright, I will explain it again. So we are considering here sending 1 bits at the rate of 9600 baud rate value. This 9600 means change of signal 9600 times per second. In a second, it change 9600 times. So instead of 9600, I can write 9600 time change per second. In mathematical expression, I can write this second in the numerator. So I have write it here, and I can express this second in terms of microsecond. Second converted to microsecond will be thousand times, right? So when this thousand times divided by 9600, we get this much microsecond. Alright, so here we are sending only 1 bit, right? So 1 bit takes this much times to send. Alright, that means if I want to send another bit, then after sending the first bit, since it takes at least 104.6666 microsecond to transfer 1 bit, I have to wait. After sending 1 bit, I have to wait for this much of time, and then I have to send again another bits, and I have to wait for this much time, and I have to send another bits. So this is actually representing the time gap between sending 2 consecutive bits. So That's the things. Okay, so that's the rate how bit are transfer into baud rate. Okay, so this 104 is integer portion rate, so we will store in the UART integers baud rate dividers register. Okay, this 104 microsecond, and then this is fractionals value, so we will multiply it by 64. We just multiplied it by 64 plus add 0.5 and then get the decimal value 11. Okay, so we will store that 11 in the UART FBRD fractionals baud rate dividers register. This one, UART fractionals baud rate dividers register, UART integers baud rate dividers register. So I store 104 in the IBRD and then 11 in the FBRD. Okay, in our call. So 11 in the FBRD, 104 in the IBRD. Okay, I believe you understand. Why did you never explain me like this? And this is CC is a clock register, and CC value equals to 0 means use the default system clock. So UART is now using the default system clock in the circuit. So when we think about when we write hardware code, we have to think about the hardware portion also. Okay, we are actually writing the coding portions, but this is hardware, so in the back of the mind we have to think about the hardware. Okay, coding is not about only software. Okay, and up to this, because I used to be a software coder also and hardware coder also, so you know I can think mainly about coding means software, but after becoming hardware coder, I began to think in the back of the mind all those hardware configuration and setup, you know. So what this line says is, and this line says UART 0 is now using LCRH register and its value is equivalent to 0x60, and 0x60 in hexadecimal is this, and 0 in hexadecimal is this, 6 in hexadecimal is this, and 0 in hexadecimal is this. So what does this mean? This line only means this, right? So here this is the D3 bits. The D3 bit is a stop bit 2 bits, and the stop bit 2 bits I didn't set. I'm just putting it 0 because I just want to use the default value. When I put it 0, that means I just want to use the default value of that particular bits. And here this bit is stop bit 2, and I'm using the default value of this bit, and the default value of this bit is to use only one stop bit in data framing, in the data frame. And I put here the D5 bit and D6 bit, set it means I put it 1 1, because putting 1 1 on this bit will has valid to do another operations. This one, okay, and this form the word len, and how it function is by setting the D5 bit 1 and the 6 bit 1, we choose here 1 1, we choose the 8 bit data, so that we can use that 8 bit in our data frame. Okay, so we are using here the stop bit to default value, so that we use only one stop bit, and we can set this WLAN by putting D5 and D6 bit 1 1 and choose 8 bit, so that we can use 8 bit and one stop bit in our data frame. Okay, the start bit is added by default, and your 3 in hexadecimal is this, 0 in hexadecimal is this, 1 in hexadecimal is this. I'm talking about this. Okay, here this line is just saying UART 0 is now using this 32-bit control register, this CTL control register, and its value is equivalent to 0x301. 3 in hexadecimal is this, 0 in hexadecimal is this, 1 in hexadecimal is this. Okay, so this 0 bit is the UART enabled bit, and I set it to 1. That means UART is now enabled. And this D8 bit, I set it to 1. This is transmit enabled bit, so now I can transmit data using the UART. This is receive enabled bit, so now I can receive data or bits through the UART transmission process. Okay, let me show that resistor. This is the resistor that UART control resistor. So this D0 bit, I've set it to 1. That means UART is now enabled. This DXE bit, the D8 bit is now enabled. So transmit is enabled. This is transmit enabled bit. So transmit is enabled. You can now transmit data through this UART now, as you have enabled the transmit enabled bit. The D9 bit is the RXE bit, means receive enabled bit. As you have set this receive enabled bit, you can now receive data or bits through the UART transmission process. This is the setup of the UART. After setting it up, I enable the UART. Now let me configure the GPIOA, because I need at least 2 pins of this GPIOA, one for transmitting the data, one for receiving the data. So 0 in hexadecimal is this, and 3 in hexadecimal is this, right? So let me explain something. This is not related to this line, but as I have chosen already GPIOA, I'm going to say about this is GPIOA pin. So I choose only 2 pins, bit 0 and bit 1. That means pin 1 and pin 2 of GPIOA. Pin 1 and pin 2 of GPIOA. Why? Because I need only 2 pins. one for TXD pins and one for RxD pins. TXD pin is the pin where we transmit all kind of data through the from the UART circuit to other device. And this RxD pins, I'm going to use this pin for RxD, and this pin RxD is for receiving any kind of data or bit stream or bit by bit from UART transmission process from other device. Now what I have explained just now is nothing related to this. I'm just explaining about I use only 2 bits of the GPIOA I have chosen, or port here. Now let me explain about this line. This GPIOA is using the DAN resistor, and its value is equivalent to 0x02. 3 in hexadecimal is this, 0 in hexadecimal is this. But this DAN resistor is just saying, whatever pin you have chosen for this GPIOA, this pin number 0 and this bit 0 and bit 1, or pin number 1 and pin number 2, whatever. Just make it digital pins, because we are using here everything digital and not analog. And then after this, this line is saying this GPIOA is now using AFS SEL resistor, and its value is equivalent to 0x03, and 0 in hexadecimal is this, and 3 in hexadecimal is this. So this AFSEL resistor is just saying whatever pin you have chosen for this GPIOA, this pin is about this GPIOA, but this AFSEL resistor is saying whatever pin you have chosen for this GPIOA, just make it not only as simple IO, but make it able to work for other functions like UART, I2C, SPI, timer, etc. This line GPIOA is now using the port control resistor, and its value is equivalent to 0x01, and 1 in hexadecimal is this, and 1 in hexadecimal is this. So it means the 0 bit and the bit D4 of the port control resistor, the 32-bit resistor, is now set, because by setting the D0 bit, we are making the bit zeros of the GPIOA set for TXD pins, and setting the bit D4 of the GPI of the port control register, okay, set the pin, okay, 2 of the GPIOA, set this pin for the RxD. RxD is a pin where we receive all kind of data or bits from the data transmission process, and TXT is a pin where we transmit all kind of data, or data means bit of stream, right? Bit of stream or bit by bit, okay, we are transmitting, okay, through the UART data transmissions medium to other device, okay. This one. So this is about configurations of the setting up of the GPIOA pins. And all this, okay, process takes at least 1 milliseconds delay. So let me, okay, wait for 1 milliseconds delay by calling these functions, and I haven't write these functions till now, so let me just write it. So I'm just taking, okay, 2, okay, variables, and then let me write the outer, okay, for loop. And let me write the inner, okay, for loop. This is very simple thing, okay. Take it simple, then everything's become simple, okay. Like that. Believe me, okay. You're just taking 2 variables, I and j, and then this is outer for loop, I equal to 0, I less than, okay, and this is 1, okay, will pass through this n as a value, and will this pass, okay, to this n as a value. So here 0 is less than n, and then here incremented that 0 and becomes 1, but here the conditions 0 less than, okay, 1 is true, so this line will execute. And how many times this line will execute is, okay, so let me explain this first. J is 0 first, and then j is less than 31 at 0's time, and j increment, okay. So this one will execute 31 at 0 time. I believe everybody knows about the for loop, okay. So until here j is 0 and j is less than 31 at 0's time, so this line will execute, okay. And before this line is execute, this will increment to 1, and here j becomes 1, and then 1 is less than 31 at 0, and j is increment to 2, but here the condition 1 is less than 31 at 0 is true, so this line will execute. So like this, it will execute until, okay, this one is j is 3179, okay, but it starts from, okay, 0, so it will execute 31 at 0 time, right? So because of that, this one before it was increment, okay, so this one become 1, and 1, okay, less than 1 is false, so this line stop executing, and this line will never execute, okay. So this whole function, okay, work like that, and it was meant to, okay, call only once, because I have right here only 1, okay. It was called only once, and this whole functions was meant to, okay, gives at least 1 milliseconds, and running this whole process, it takes 1 millisecond, and this value 31 at 0's time is calculated so that this whole function in executing takes at least 1 millisecond still, okay. by making more decay delay here by executing this line 31 at 0 time. Okay, it makes this whole functions to take 1 milliseconds in executing. Okay, from here to here. Okay, so this whole functions give at least 1 milliseconds delay, and I'm calling only one time, so we get only 1 milliseconds delay because okay, it takes 1 milliseconds at least, okay, in executing all this line. And executing means setup, okay, all this hardware, okay, process. And here I'm writing, okay, the for loop to call our transmitting functions. Let me call our transmitting functions. I haven't write these functions. Yeah, we set up everything, so I'm calling that transmitting functions to transmit our data, but I haven't write these functions, so let me, okay, write the functions here. I'm pausing C because this is the data I will want to send. So, and here I will write. This is very simple, but listen carefully, okay? So what does this line says? This line is saying UART 0 is now using the flag register, that is FR, and its value is equivalent to 0x20. And 2 in hexadecimal is this, and 0 in hexadecimal is this. I mean this 2 in hexadecimal is this, and 0 in hexadecimal is this. So this line is saying UART 0 is now using FR register, flag register, and that register value is equivalent to 0x20, and 0x20 in hexadecimal is this. Sorry, this one should be 0, and this, okay, only mean this bit, okay, and this bit. So this whole line, it only means this bit, right? So what is this bit? This bit is, okay, transmitting flip-flop full flag, and let me, okay, tell you about that flag. So this is the transmitting flip-flop full flag, the D5 bit of this UART flag register. So let's say, okay, what happened in transmitting flip-flop full flag, okay? When you want to transmit a byte of data, you place that byte in the data register, and after that, that byte is shipped to the UART buffer register. And after this, the transmitting flip-flop full flag is set by making its value 0, that means lower. Okay? Remember, this flag is set by making its value 0, lower. Okay? 0, right? So that's why it says it's not equal to 0. But it should be 0, right? So we write here while. While means it will be 0 after some time. That means this will be 0 after some time, but it is not 0. That means this transmitting flip-flop flag will be 0. That means it will be set after some time, but it is not 0, so it is not set right now. Okay, but the while says it will be 0 after some time. The while express says it will be 0 but not 0. Still it will be 0. After some time it will be 0. So there is some time that we are waiting. And what we are waiting is, as I told, the data to be transmitted has to be passed in the data register, and it has to be shipped to the FIFO buffer. And after that, this transmit flip-flop full flag will be set by putting its value 0. So we are waiting for that data to be stored in the data register and finally get shipped that data to the FIFO buffer. We are waiting for that much time. Okay, and after that, this transmit flip-flop flag will be set by putting its values 0. So this will be 0. After some time, then the flag again will be set. And what happened after the flag is set? After the flag is set, the byte you have put in the buffer will be framed between the start and stop bit and will be transmitted by the TXT pin. As I have told, the TXT pin is the pin where we transmit all kind of data or bit stream or bit by bit, okay, from the UART circuitry through the UART transmitting medium or transmitting process, okay, to other device, receiving device, right? So here the flag will be set after some time, and after that the data will be transmitted, right? So here we will write UART 0 implies GR equal to C. And what does this mean? This means UART 0 is now using DR register, and the byte placed in the DR register is 0. As I have told, I have passed this C, the byte to be the data to be transmitted, and this is just that data that I put in the data register. As I have told, I have to place the byte to be transmitted in the data register at first, right? And will be shipped later to the buffer. And okay, so that's the data. This is C that is placed in the data register. And this line UART 0 implies DR. What does it mean? It means, okay, UART now is using the DR register, right? And this DR register is a register, 32-bit register, where every data you want to transmit should be placed in this data register, because this is the register, okay, if any byte or data is placed in this data register, it will be transmitted. So it is compulsory you have to place any kind of byte or data you want to transmit to be placed in this data register, because everything kept in this register will be transmitted. Okay, so we are writing here UART 0 is now using data register because the data will be transmitted. Okay, because whatever kept in this data register, DR register, will be transmitted. After it is shift to the buffer, okay. But what we consider in general is, if we used the DR register, then the data will be transmitted. So here the flag will be set, and then here the data will be transmitted. Okay, so that's the transmitting functions, and here I call that functions, and I want to transmit A. Okay, let's transmit only this A, as it is our first code, and here A, the ASCII value is 41, and 4 in hexadecimal is 10, and 1 in hexadecimal is this. So this is the binary values of this A, and this binary values of A, this is bit by bit, okay. this is a bit stream, one bit after another, okay. And so, but here this is the lab bit, right? In UART, lab bit is sent first. So this one, okay, the lab bit will send, and this is the MSB bit, it will be sent last, okay. So here, okay, before the lab bit, the stop bit will be, okay, put, and after this MSB bit, the stop bit will be put. We use only one stop bit, right, here, because where is that? Because in this line the D3 bit is stop bit 2, and we put 0, that means use the default value. So the default value of stop bit 2 is use only one stop bit, right? And here this bit D5 and D6 says it is WLAN, and WLAN says to use 8 bit, right? By setting this 2 bit, it means to use 8 bit. So we use this 8 bit, and then one start bit here, it will be put by default, and one stop bit here, okay. So it will be, okay, send bit by bit, this bit stream, one bit after another, but it will be sent in the UART transmissions medium at a rate of this much, okay, at the rate of 104 plus 11 microsecond. That means 104 plus 11 microsecond. First, okay, the start bit will be sent, and it will wait for 104 plus 11 microsecond. Then the LSB will be sent, and it will wait for 104 plus 11 microsecond, and then, okay, the next bit will be sent, and it will wait for 104 plus 11 microsecond, like that. So in this way, okay, the bit by bit or bit stream or data will be, okay, sent through the, okay, UART transmission process. So thank you all for this session.